Okay, so last time we talked about evidence such as we have for there having been a fairly Earth-like hydrological cycle on early Mars, and that might include river valleys and perhaps an ancient ocean. What I want to talk about today is a little bit about how we got from there to where we are now with Mars. As I said, Thursday we will jump the line a little bit, and we will do this simulation of the Viking biology experiments. But next Monday, I'll go back and finish up with water by talking about what we actually know about water on the planet today. But this transition between Mars of the past versus Mars of today is important. And so as we talked about last time, when we talked about the valley networks, and evidence about whether they were surface river systems or groundwater sapping, and with the idea that it's looking more and more like real river systems that used to be present on Mars. That led into talking about oceans. So given that the quiz is fresh in your mind, what are those different lines of evidence that we have that Mars used to have an ocean?
The frozen water.
What about frozen water?
They found like frozen water like certain parts of the surface.
Okay, so if we look, we see things like patterned ground, and we'll talk more about this next Monday. Those areas that are broken up in these big polygons, subsurface ice.
How about the thing, I forgot what they were called, but they look like empty rivers, kind of.
Okay, so those would be the valley networks. They look like empty rivers, and if there were rivers, then a consequence of having rivers would be they need a water source, and the rivers go somewhere, okay? So that's kind of,
Professor,
yeah.
would they ever like stop sending stuff to Mars, like when they stop knowing stuff, or like, because what if like there is Martians and they destroy the planet and like stop?
Pretty clear that there was not Martians. We don't know whether there's microbial Martians, and that's what we'll be talking about in the next few sessions. Yeah, so the U.S., Europe, China, Russia, they could all decide to stop sending missions. It's happened before. After the Viking missions, we didn't send a mission to Mars for 2 decades because we got bored with Mars. But currently Mars is somewhat in vogue. We have a problem, though, in that after the Maven mission and the InSight mission, which is the next lander, and the Mars 2020, NASA doesn't have any further Mars missions on the books, although that may change. What other evidence for oceans?
The sea line or the shore that seems to go around the northern hemisphere.
Paleo shorelines. Okay. If you've got an ocean, it's going to create wave action and leave its mark. And those shorelines were all, for at least one of the contacts, were all at equal level, as you'd expect for shorelines. Is that what you're going to talk about, Jeff?
Yeah, but I can stand the whole.
Okay.
I don't know what it's called, but like usually when the river ends, they have that smoke of all the sediments entering the water source. Don't know if that's
Okay. So there was a study looking at these delta structures, and those that seem to empty out into the this big open area also seem to be at the same level. So, that is Mars that looks a lot wetter, clearly, than Mars is today. It's still debatable how warm Mars was, whether Mars was ever as warm as, you know, we are comfortable living with here on the Earth, or whether, you know, maybe it was a wetter planet, but still cool, or at least not warm enough for, you know, this ocean to be an open tropical kind of ocean. It could be ice-covered Arctic kind of ocean. So this is still really much an open question. But clearly Mars is not like that today. And so somehow Mars must have changed. And I want to go through just some of the aspects of what that transition was like, and what are some of the missions that are collecting evidence to tell us about that transition. Okay, so just to put this again into some context, we talk about Mars being broken up, the history of Mars being broken up into these three main eras: the Noachian, the Hesperian, and the Amazonian. The boundary areas between those are shifting back and forth a little bit. This figure is actually a little old, but clearly, if there was a warm and wet Mars, it was restricted to this earliest time period of the Noachian. And we want to understand what happened to Mars. Why didn't it stay Earth-like if it was Earth-like early in its history?
That was 4 billion years ago.
Yeah, about 4.5 to a little under 4 billion years for the Noachian. One thing we see during the Hesperian and a little bit into the Amazonian is we don't see those valley networks anymore. So, you know, if there was rainfall leading to river channels, that was really constricted to the Noachian. But we see, in addition to the valley networks, one of the early features that were determined from orbit by the Mariner 9 images and the Viking images are these things called outflow channels. And so I want to spend just a little bit of time talking about that and how they might tell us, what they might tell us about this transition. Then what I really want to focus on are the Opportunity and Spirit missions, as well as a couple of the Order missions that are telling us a little bit about this history of water. Okay, so I think we mentioned these outflow channels before, but we haven't discussed them the same way we've talked about the valley networks. They are also appear to be channels that are carved by flowing water. But in the case of these outflow channels, we're not talking about, you know, rain-fed, you know, precipitation running across the surface of the ground and forming these channels. What we're really talking about are catastrophic floods. I'm not sure if I'm spelling that right, but catastrophic flooding. Something happened during this middle time period on Mars to periodically release huge volumes of water. Volumes of water that would dwarf, you know, the kind of water flow that we see in the Mississippi River or the Amazon basin or anything like that. These are huge releases of water, and they flood across the landscape. They carve these structures. That's why we get this kind of streamlined teardrop structure as the floodwaters flow across the landscape. And so the questions would be, well, what would the questions be? If that is the situation, if these outflow channels are formed by massive catastrophic flooding, what would you want to know?
What caused the flooding?
What caused the flooding? I mean, how much water was involved there? You know, hundreds of, it's always dangerous to say a figure off the top of my head, but, you know, clearly cubic kilometers of water are somehow released at a short period of time, and those rush across.
Is it at all possible that Mars once had like a larger moon that could have influenced the oceans more, or no?
You'd have to, well, first of all, there's no evidence to suggest that that
Yeah,
is
never
the
happened.
case.
Okay.
If somehow Mars did have a large moon in the past, you'd have to come up with, well, what's the mechanism for getting rid of a moon, other than having a Death Star come up and blow it out of the sky?
I mean, that's likely, right?
There was two of them.
There was two of them, yeah. Phil Plait, who ran the Bad Astronomy blog for a long time, one of his books that he put out is just different ways you can destroy a planet. And it is really, really hard to completely destroy a planet. I mean, we could screw up the ecology of our planet and so forth, but to actually physically destroy the Earth or the Moon, it takes a lot of energy, and there are not a lot of physical mechanisms that could do that. Now, if the Moon formed too close to Mars, like is the case for Phobos, our Moon is far enough away that it's gradually getting further and further away from the Earth, and the Earth is slowing its spin, and over time, the Earth will get out to some stable point and park there. Phobos, one of the moons of Mars, is below this limit, so that it's actually getting closer to Mars each year. And so in a few 100 million years, Phobos will be plunging into Mars and causing a new impact crater. But, you know, whether a large moon would have done that, I'm not, yeah. Okay, so source of the water and what would be available for releasing the water. We do see, associated with many of the outflow channels, this area, this type of area that's known as chaotic terrain, where it looks like the landscape has just collapsed, and there's all this rubble of blocks of rock and so forth that are left after this collapse. So if you see an area of collapse that's up at the head of these outflow channels, what's your likely interpretation for the source of the water for the flooding?
I would say groundwater sapping.
Well, not so much groundwater sapping, because that's kind of a gradual process that works uphill, but
Kind of like a lake or something like that.
a lake on the surface?
Yeah.
No.
Okay.
What we're really talking about is somehow a release, a catastrophic release of an underground huge reservoir of water.
Okay.
Okay. So we see, we actually have similar kind of terrain here on the Earth. I don't know if any of you have been out to eastern Washington State. I've not. You have? Okay. Are you familiar with the scablands? Okay. There's this terrain out in the eastern half of Washington State called the channeled scablands. Scablands is a really attractive term for your landscape. But it's essentially an area of the state that appears to have been massively scoured by huge catastrophic floods. And this was a story that was also an example of a lone voice out in the wilderness pulling together bits and pieces of this information. Harley Bretz was geologist. I forget, he was out west somewhere, Montana, one of the Montana schools, I think, and came up with the idea that the best way to explain all of these structures that we see in this channeled scablands area is a massive catastrophic flood that came across the landscape, carved these kind of streamlined channels. If you take a look at this picture down here, this is a semi-truck. And these are essentially ripples in the of sand left by the flooding. Okay, so if you've walked across the beach, you might have seen small little ripples that the wave action makes. Well, imagine waves of water that would make ripples that are much more massive than this semi-truck that's going by the landscape. So again, huge volumes of water just pouring across this landscape and cutting. In the case of the channeled scablands out in Washington State, we know where the source of the flooding is. During the ice ages, periodically ice sheets would come down from Canada and block off the major rivers that are flowing out to the Pacific Ocean and dam up huge amounts of water behind those glacial sheets. In particular, there's a glacial lake Missoula. I think it's OUL. Oh well. So the glaciers would periodically come down, dam up the river, create a huge lake behind the ice dam, and then as the glacier is receding, it doesn't necessarily just gradually melt away and then release the water that's dammed up behind it as this trickle. What happens when the ice dam fails as the glacier is breaking up?
Just goes all at once.
All of that water that's dammed up behind in Lake Missoula just goes flooding across. Now that's probably not the case of what's happened on Mars, because these outflow channels have occurred way past the time when we had those valley networks being produced. But instead we've got a proposal for a different way that these floods have built up. Okay, first of all, I think I pointed this out before. Again, these are the outflow channels are in red here, and they tend to be flowing from the southern highlands and pouring down into the northern lowlands or down into the Hellas Basin area. So clearly a difference in elevation appears to be involved in the conditions that set up these floods. So what I want to do is walk you through this theorized change about how the hydrological cycle on Mars has changed over time. Starting with back in the Noachian, when we were talking about a warm or warmish wet Mars. And if there was indeed an open ocean in the northern hemisphere, evaporation from that ocean would be the source of the water that would fall down as rain or as snow and complete the hydrological cycle through surface flows or through groundwater. As Mars cooled off, and we know it would have cooled off to get to current conditions, over time you get the buildup of what's known as cryosphere. Cryo meaning cold, and sphere just meaning, it's like biosphere or atmosphere. But this cryosphere, this layer of ice that shuts off the groundwater from the atmosphere, covers over the surface of the ocean, and as the limited amount of precipitation and water cycle continues, instead of having rivers carry that water back to the northern lowlands, it's, for example, deposited as polar ice caps, and that ice accumulates. At the base of the ice, it's warm enough for the ice to melt, so what will happen to the water at the base of that ice cap? Gravity's going to pull it which direction? Down. Okay. So you may have this frozen precipitation accumulating, melting underneath, accumulating pockets of water underneath the area where it's frozen. And over time, that water can build up behind the ice that is separating the groundwater system from the atmosphere. Well, if that ice fails, what's going to happen?
It would fall into the ocean.
You're going to have water gushing out from this underground reservoir, and it's going to head downstream, carried by gravity, and that's generally going to be carried into the lowlands, and it's going to be scouring the landscape along the way. So this gradual cooling out of Mars, this gradual separation or locking off of the underground water from what's going on above is a reasonable model for how Mars would have changed over time, and it does help us to explain how you could get this catastrophic flooding. You know, maybe a meteor hits here and fractures the crust and releases a lot of that pent-up groundwater. Maybe the hydrological pressure. You've got so much weight of water behind this ice that the surface of the Earth of Mars just fails. Whatever happens to release that water, it's going to rush across, leading to those kind of outflow channels. So we see a lot of this outflow channel activity during that middle Hesperian era. We see some outflow channels that appear to be later on into the Amazonian, but over time, the level of this outflow channel activity has decreased. Mars is just getting so cold now that it's difficult to accumulate enough water in these underground reservoirs with a thin enough sheet of ice in front of it to actually fail and lead to these catastrophic flooding episodes.
Professor?
Yes.
Is this the only hypothesis about the outflow channel?
Some flavor of this is pretty much what is thought to have happened. There's some, it could be that there's less of a liquid water reservoir and more just ground ice, and something like a large impact rapidly melts enough of that subsurface ice to lead to large volumes of water flowing out. But clearly the water is, for these outflow channels, is being released from underground reservoirs, because there's really no other place during Hesperian Mars, or certainly now during the Amazonian, to accumulate large quantities of water on the surface of Mars. Okay, what I want to turn now, though, is to the rovers, Spirit and Opportunity, which is why we looked at that Colbert clip earlier. So this mission was basically an attempt to recover from a couple of failures early in the aughts, the 20 aughts. Okay, so after we returned to Mars with the Pathfinder mission in 1996, NASA thought they would ramp up Mars exploration because people were interested in Mars again. We had just had a big press conference about the same time that Pathfinder arrived at Mars, where scientists from NASA have announced evidence for life in a meteorite from Mars. President President Clinton, made a big announcement from the White House saying, wouldn't this be fantastic if there was life on Mars? So NASA started ramping up their Mars program, and at the next launch opportunity, they plan to send both an orbiter and a lander. The Mars Polar Lander and now I'm blanking on the name of orbiter, but they were 0 for 2 during that launch window. Okay, the orbiter burned up in the atmosphere because Lockheed Martin were using English units of measurement, and NASA was using metric units of measurement. And so rather than hitting the top of the atmosphere and slowing down, plunged right in the atmosphere and burned up in the atmosphere. Why does everyone just use metric? I don't know. And then this is the area of faster, better, cheaper. When NASA was going to do more missions, they were going to do them faster, they were going to make them cheap, and they were going to be better missions. Well, they were faster and they were cheaper, but they weren't necessarily better. It's like you can pick 2 out of the 3.
Yeah.
And if you go for faster and cheaper, you're not necessarily going to get better. And so the Mars Polar Lander never had a complete end-to-end test of its integrated systems. So if you're coming down and landing on Mars on a retro rocket, how do you know when you need to turn off the retro rocket? You have to have some signal to the probe that you're down on the ground.
I mean, I'm sure it's got rocket science.
And the easiest thing to do is when the foot pads hit, trips a little signal and tells the computer, turn off the retro rocket, otherwise you're going to tip the... Well, it turns out that when the rocket's coming down when the probe is coming down on its retro rockets and it flings open its landing struts, that was enough of a signal to tell the computer that, oh, we're down on the ground, let's turn off the engine when you're still hundreds of meters up in the air. And so then what happens to the probe?
It just
Falls to the ground and crashes. And so it was not a good time for NASA.
Is that crash ice still there?
Yeah.
We just littered on Mars.
We have littered on Mars.
We littered everywhere.
We and the Soviets have littered on Mars since the late 60s. Okay. So NASA took a break. It pulled back the next mission that was going to be going in the next launch window, and said we need to review this faster, better, cheaper approach. And so they put out a call for proposals for new mission designs. And Steve Squires, who we looked at in the clip, proposed taking this basic rover design and submitted that for this 2003-2004 launch window. And NASA said, we better go back to the way we used to do, and we'll send 2 just to make sure that at least one of them gets there. So this was a fairly big investment on the part of NASA. The basic rover design here. We have these solar panels, which provide what? Power. 6-wheeled rovers with this rocker bogie mechanism that allows it to kind of climb over rocks. Clearly antennas for talking back to mission control, generally through orbiting spacecraft. So we have a low gain antenna and a high gain antenna. We have 2 panoramic cameras on the top of this mast, giving it a very much anthropomorphic, where's Wally kind of look. Why have 2 cameras at the top of this mast? What? Okay, this mast is about person height, and there are 2 cameras. What can you do with 2 cameras that you can't do with 1 camera?
Pictures at once.
What can you do with 2 eyes that you have more difficulty doing with 1 eye? What?
Look at different.
It's a
view?
Field of, it's not so much, the rover's not looking at two different objects like a chameleon.
Missed something that the first one didn't.
Is it literally depth perception?
Depth perception,
I
okay.
just said that jokingly, I didn't know. It was
No. So when you have two cameras, you can do stereo imaging, and you can build up a 3D image of the terrain around. And so not only does this give us, this 3D image of the terrain that the rovers are moving through, but because the mast just happens to be, at about 5.5 feet, the views from these cameras give us really kind of a view of what it would look like if we were standing there on Mars. In terms of the science package, well, the PanCam cameras are clearly part of the science package. Then there is this mini thermal emission spectrometer.
It's a mouthful.
It's a mouthful, but it basically is another camera system, but based on the infrared radiation that is being emitted from rocks and so forth. So we can just say mini TESS, thermal emission spectrometer. This basically provides information on mineral composition. Different minerals emit different wavelengths of ultraviolet light. Different minerals will absorb different wavelengths of ultraviolet light. So infrared light. So by looking at the infrared radiation coming off of the rocks that are around, the rover can make some analyses of what minerals are in those rocks.
What do they
What?
What do you find, like, is there like a common mineral?
Well, we'll talk about where Spirit and Opportunity were sent. They were sent to different areas for different reasons. Opportunity was actually sent to Mariana Planum because a similar thermal emission spectrometer from orbit on the Mars Global Surveyor picked up the signature of a mineral called hematite, which is a mineral on Earth that's normally formed in the presence of hydrothermal water activity. Okay. So also the rovers have this arm that has a rock abrasion tool for grinding into below the surface of the rocks. Oftentimes the surface of the rocks get weathered, and you really want to know what's the rock like inside, where it hasn't been weathered. So a geologist would walk around with a hammer a rock hammer in order to be able to break the rock into pieces to be able to see on the inside. No not rock hammer wielding robots on Mars. Instead, there's this kind of grinding apparatus that would take off the surface layers of rocks to be able to look inside. And then there's basically a microscope that provides very fine, detailed images of the rock structure. And two other spectrometers, this Mossbauer spectrometer and alpha particle X-ray spectrometer, or APXS, which is also what was on the little Sojourner rover that was sent, previously. This essentially tells elemental composition. So whereas the thermal emission spectrometer tells what minerals are there, this can tell what elements are there. Is there calcium? Is there, whatever. The Mossbauer spectrometer is specifically set up to look for iron minerals. And again, as we talked about, the missions both landed in January 2004 and survived several Martian winters, which they weren't expected to do. The operators got very clever about parking them in nice sunny spots facing toward the equator, and so they could charge up their solar cells during the winter. And everyone was very surprised when both rovers survived the first Martian winter, and then, like I said, Spirit survived until 2011, when end of mission was declared, and Opportunity is still going today. Okay, let's talk a little bit about Opportunity first. Opportunity landed in Eagle Crater in Meridiani Planum. Happened to bounce right into the equator. It's being sent hundreds of millions of miles from Earth to Mars. How many of you are familiar with how these rovers got down on the surface of Mars?
Parachutes.
Not parachutes. Well, parachutes, but not the final step.
They used like rockets to.
Not rockets. No rockets landing these guys.
Magic.
Airbags. There were rockets, there were parachutes to get the carrier down a few tens of meters above the surface of the Earth, of Mars, and stationary. Then they inflate these airbags and drop the pod. And they're bouncing like half a kilometer in height until they eventually settle down. And then once the probe has stopped, the airbags deflate, the pedals unfurl, and the rover crawls out. Well, Opportunity happened to bounce, after all of this, right into a crater where there was bedrock for it to do its analysis. Spent some time there, then went to Endurance Crater. We'll talk a little bit about Endurance Crater. Then thought, well, there's no way that it will ever make it, but after Endurance Crater, the next most interesting thing is Victoria Crater here. So it spends a couple of years going across the surface of Meridiani Planum to get to Victoria Crater. Spent some time in there, went down in the crater a little bit, did some studies, and then got tired, bored with Victoria Crater, and said, well, there's no way in hell that we'll ever make it to Endeavour Crater, but that's the next most interesting thing. So let's take off, and over the course of, again, about 2 years, it finally made it, and Opportunity is now working its way around the rim of Endeavour Crater. Why are craters interesting if you're sending a rover around looking for stuff? If you go out in the field with a geologist just today, they'll probably take you to a road cut where a road is cut through this area, so you can see the different layers of rock that are exposed by the road cut. Or they might take you to the Grand Canyon where you can see all the layers. We don't have any road crews on Mars. We don't have any drilling rigs on Mars that will bring up cores of sediment. So what do craters do for us?
Show us the different.
They excavate subsurface layers. So without the craters, Meridiani Planum would be this kind of boring, vast, flat plain. And so by looking at all the craters, Opportunity is able to look at different levels of rock that provide different information about the history of water, which is essentially what Spirit and Opportunity were both were the primary goals for their missions. Okay. And I mean, there are literally hundreds of scientific papers that have come out of these two missions, so we're not clearly going to go through all these. Let me just point out some highlights here. These are some, one of the most obvious things that that they noticed at Eagle Crater, where Opportunity first landed, were these little things they call blueberries. Really aren't blueberries.
who names these things?
The mission team basically gets to name things, and so, for the Pathfinder mission, one of the main rocks that they looked at was called Scooby-Doo, because I'm running the mission, I get to call it whatever I want, right? So, these blueberries are really what's known as concretions. I won't go through all the details, but here's actually some of the data from the Mossbauer spectrometer that was again sent on as part of the instrument package to look specifically for iron-containing minerals. And those blueberries, those concretions, are very rich in hematite, which was the mineral that Opportunity was sent to verify was there. And these are evidence of past activity of water because essentially the concretions form when you get minerals precipitating out of a watery groundwater in an area. So something happens to start this hematite-rich granule to form, and as other groundwater percolates through the area, additional iron and other minerals precipitate out and form this concretion, and it gradually grows over time to form this structure. So in order for these minerals to be precipitating out of water, clearly there had to have been water there. So very important evidence for groundwater, at least at this site. Also at this first site, the microscopic imager found evidence of these cross-bedded laminations. Basically layers that had been laid down one after the other. This diagram here kind of shows you the situation. These cross-bedded laminations can be either deposited by wind or by water, but based on the size of the grains involved here, these were argued to be deposited by water. So you have to have flowing water going across the surface of this landscape, however many billion years ago when these rocks were formed, to lay down these layers of finely stratified material as the waves, as the water is flowing across the surface. So very early in its mission, Opportunity got to check off the big boxes. Yes, evidence of past water on Mars. These concretions, the mineral composition. We find minerals like jarosite that are only formed in the presence of water here on Earth. So, given the suite of instruments that Opportunity has on the rover and the way it's looking at the rocks, it has very good evidence early in the mission that there was water, certainly groundwater, and probably some surface water in this area in Meridiani Planum in the past. Opportunity spent a lot of time at this Burns Formation in Endurance Crater. Endurance Crater was the second big crater that it went to after Eagle Crater, which was really actually just a dinky little crater. And in Endurance Crater, Opportunity basically climbed down the slope. Took them a long time to get comfortable with the idea of sending the rover down this slope. And they would, at various points, drill holes in the rock using the rock abrasion tool, and they would make measurements of the mineral composition and so forth. And from that sequence of samples, they could build up this, what geologists are interested in looking at, this stratigraphy of the site. I won't focus a lot on the details of the stratigraphy, but there are lower structures that are basically ancient sand dunes that then got covered over by sheets of sand that were probably laid down in a watery kind of environment. And then there's some material at the top. And part of what's very interesting here is that there is evidence that groundwater modified some of these lower layers of the rock sediments. So as the groundwater comes up, it's going to dissolve some minerals, it's going to deposit others, it's going to leach some minerals out of the layers altogether. And so the information at Burns, again, provided good evidence for groundwater in the past. Also, this is here just to remind me to let you know that throughout this area, opportunity is finding minerals that have high concentrations of sulfates, which will be important as we interpret this, what's going on here. Okay. Eventually, opportunity gets to Victoria Crater, and again, it's kind of more of the same, but on a larger scale. Again, there are new science observations and new papers, but nothing I think that we need to concern ourselves with too much. The main point here is that in all of this, the information from Eagle Crater, from Endurance Crater, from Victoria Crater, we get a picture of Meridiani Planum, this area on Mars, some 3.5 billion years ago, where there is some water around. This is not actually a picture of Mars, but this is the kind of habitat that might have been present in Meridiani Planum about 3 billion years ago. Low playa, lake bed kind of areas, so shallow waters. Shallow water that would be blown by the wind, leading to those depositions of sand and other material. Certainly a lot of activity of groundwater. But the high sulfates indicate that this water at this time was highly acidic. I mean, this is more than vinegar acidic kind of water. Okay? This is more kind of sulfuric acid kind of acidic water. So, opportunities sent to Mars to look for habitable environments and to look for water, but water by itself doesn't necessarily mean habitable environments. So this area in Meridiani Planum, because the water, the groundwater, the surface water was probably so acidic, it's probably not the nicest environment for little critters to be living in. However, with the multi-year journey to Endeavour Crater, where opportunity is now basically by sending opportunity to Endeavour Crater, it's sampling an entirely different part of Mars history. For a variety of reasons, we think that the area surrounding Endeavour Crater, and certainly the layers exposed by this large crater, are exposing much older Martian terrain. And that's where opportunity is now. It's been working for the last year and a half or so, looking at different mineral outcrops and so forth. But I kind of said here, this is really an entirely new mission as far as the geology that they're looking at.
So no conclusions yet.
Well, the main conclusions, what we're finding both from orbit, which is what this picture is, and from the data that Opportunity is collecting, is that we're seeing or getting evidence for a lot of clay minerals. And this is important because you don't form clays under acidic conditions. Clays will form under more neutral pHs. And so the clays are again evidence for water, but this is water you would much prefer to drink compared to the water that was the evidence for water that Opportunity found earlier. So by going back further into time, we get much more evidence for a much more habitable environment. The early sites in Meridiani Planum that Opportunity looked at were kind of nasty, very acidic, kind of dry, not evidence for a lot of water. By going back further in time, by looking at these older deposits, Opportunities finding evidence for a much more benign environment, a more neutral pH, a watery environment that you could actually imagine things living in. So that's the take-home message for that part of the mission at this point. And if the lights don't get shut off for budget reasons in the new budget cycle, Opportunity could spend years here at Opportunity Crater, at Endeavor Crater, looking at different features. I'll say a little bit less about Spirit. Spirit was sent to Gusev Crater. Because it looked like it would have been a lake in the past. Gusev Crater has this tributary going into it, and this outflow channel, not a real outflow channel, but a channel coming out from the crater as well. It looks very much like a place where water would have accumulated back in the day when there was a water cycle on Mars. And so Opportunity was sent to Meridiani Planum to check out the hematite. Spirit was sent to Gusev Crater, hoping to find lake bottom sediments. Sediments that were laid down at the bottom of a lake, because that would obviously provide excellent evidence for water in the past. Spirit landed in Gusev Crater and found nothing but volcanic rock. So clearly what has happened to Gusev Crater since the time it was a lake bottom?
Erupted.
Some lava flow came in, and the whole place got basically covered in kind of boring basaltic lava flow. Okay, so that's a real bummer. You get this mission successfully down on the ground, expecting to look for lake sediments, and all you find is lava flow. So again, expecting Spirit only to last 90 sols, and having nothing really to see in Gusev Crater where they landed, they sent it off toward these hills on the horizon called the Columbia Hills, which are named in honor of the Columbia astronauts that died when the mission failed, without any idea that they would be able to make it there. The Spirit actually had to spend a winter out in the hinterlands before, but once they got Spirit up into the Columbia Hills, they did actually find some information, some evidence for water. I just want to point out two things. One is this kind of accidental discovery. One of Spirit's front wheels locked up early in the mission, which is kind of a bummer. So the way you deal with that when you have a 6-wheeled rover is you start driving in reverse. right? And driving in reverse is just as easy as driving forward. And you drag the wheel that's not moving behind you, what's that wheel going to do? It's going to dig. Okay? So there was no trenching tool that was sent with these rovers. This busted wheel essentially became a trenching tool, and at several points in Spirit's traverse, it, clearly the wheel would move away the top sediments and show what's underneath, and this light-colored stuff here is silica. In particular, it's a kind of silica that's formed in the presence of hydrothermal activity, like geysers. Like if you were out in Yellowstone and you saw the little geyser areas, those conditions would be conditions that would lead to the production of this amorphous silica. And so just by accident, Spirit unearthed literally this evidence of hydrothermal activity on Mars. So why are we interested in hydrothermal activity? Hydro means water, thermal means heat. Okay, hydrothermal areas are ideal areas for little kinds of microbes to be living. So the other thing about water and Spirit that I just want to mention briefly is something that was found again early in the Columbia Hills part of the mission. These Comanche outcrops in particular. Were where Spirit came across evidence of carbonate minerals. Carbonate minerals are important in terms of water because they form in the presence of water. Limestone, coral reefs, white cliffs of Dover are all carbonate minerals that are related to minerals being put down in the ocean. So it's kind of it's been a big question mark for a long time. It says carbonate, CO3. If Mars had an ocean in the past, and Mars's atmosphere was full of carbon dioxide, people have been asking for a long time, why don't we see big layers of carbonate minerals like we would expect to find if the Pacific Ocean or the Atlantic Ocean dried up? We would expect to see lots of carbonate minerals being produced. We've had actually very little evidence of carbonates forming from the images and data we collect from orbit. So the fact that Spirit actually saw carbonates is an important finding.
When was this?
This would have been probably in the 2008, 2009 timeframe. The silicates were late in Spirit's mission, down near the place where it eventually got stuck. So that would have been 2010, 2011. So with that, we'll bring it to a close for today.